Rao Bhim section 9.3, we are continuing with it. In that section, we have the following result. If A is a real symmetric matrix, then A is congruent to a diagonal matrix. That is, A is P transpose dP for some non-singular P. Now, we have already commented that this result is an immediate consequence of the spectral decomposition result, because there we know that every real symmetric matrix is orthogonally similar to a diagonal matrix. So, I can also take P to be not only non-singular but also orthogonal. But we have mentioned that computationally that one is much more difficult to obtain. But if we relax our condition from orthogonal to just non-singular, then we can have a much simpler algorithm. Now, Rao Bhim has given us one such algorithm that Rao Bhim calls algorithm 9.3.2. Now, this algorithm is a very typical Rao Bhim algorithm. It is very difficult to understand what is going on. In fact, the same idea may be done in a much more simpler and intuitive fashion. So, instead of explaining the way algorithm 9.3.2 has been explained in the book, I shall explain it in my own way. So, the algorithm may slightly differ from what they have given. In fact, there are so many equivalent ways of doing the steps. They are not all same, but they will lead to basically the same result. So, we are interested in this relationship A is equal to P prime dP. Here, A is the input and the output will be D as well as P. So, if I know P, I know P transpose. So, I want to find D and P given A. Clearly, there is no unique answer to this. For example, if I just multiply P by 2, then this gets multiplied by 2, that gets multiplied by 2, and you can adjust by dividing D by 4. So, non-singular matrices remain non-singular, diagonal matrices remain diagonal, even if you are multiplying things with a scalar. So, there is no question of uniqueness. I just want to get some such P and some such D. Now, you can just bring this on this side. So, I can think of it as P transpose inverse. So, that since this is just some arbitrary non-singular matrix, I can think of it as QA Q transpose is equal to T, where Q I am taking to be P transpose inverse. So, if I take this P prime on this side and this P prime on this side by inverting, I get this. So, instead of saying that we want to find P and D, it is as well to say I want to find Q and T, because knowing Q is same as knowing P. You just invert and then take transpose, you will get one from the other. Now, what we shall do is the following thing. Whenever we are pre-multiplying, that is multiplying A from the left by this matrix Q, we are basically performing certain row operations. So, pre-multiplication performs row operation. And when I post-multiply from the right by the transpose of the very same matrix, I am doing the corresponding column operation. Thus, if pre-multiplying by Q adds the first row of A with the third row of A, then Q transpose will do the same thing to the columns, add the first column of A to the third column of A. So, whatever I do to the rows, I must do to the columns, and that will preserve the symmetry structure of the matrix. Now, what I will be doing here, I will construct Q out of some very simple operations, and the simple operation will be adding a non-zero multiple of one row to another. So, this is the operation that we are going to do. Now, when we studied Gauss-Jordan elimination or Gaussian elimination, we already know that this was one of the elementary row operations. So, this is actually non-singular operation. That is, if you do this, you can recover your original rows from this. Now this is what is done by Q. So Q transpose will do just the same thing for columns. Add a non-zero multiple of one column to another. Now let us see how we do the algorithm by taking a simple example. Suppose this is my matrix A. It is a real symmetric matrix. I have shown some of the I have shown the diagonal entries, and I have shown just one of diagonal entry. The others may be there, may not be there, that is, they may be 0 or non-zero. I do not care. Just to illustrate, I have shown one non-zero of diagonal entry. So if it is here by symmetry, this must also be the same thing. Now remember what we want to do. We want to carry out elementary row operations here and the corresponding column operations such that it becomes diagonal. Now diagonal means all the off-diagonal entries must be 0. So I will show how you can turn some off-diagonal entry into 0. So I have shown you one sample of diagonal entry. So this is 6. So what do? I can do two things. I will first take a look at the corresponding diagonal entry. So if this is the ijth entry, I will consider either the ith entry or the jjth entry. Suppose one of them is non-zero. Well, in this case, both of them are non-zero, so you can do whichever way you like. Suppose I will pick this. What I will do is, I will subtract a suitable multiple of this row from this such that this is destroyed. And you can see very easily what I have to do. I have to subtract 3 by 2 times the first row from this in order to destroy this, because 3 by 2 times 4 is equal to 6. So once you do that, remember everything else remains unaltered. So this now becomes 0. These things also become, they also change. In particular, this thing also changes because you are subtracting how much? 9 from it, right? 2/3 of this is 9 and you are subtracting from this, so minus 11. So this is the effect of pre-multiplying by, I will call it Q1, the first operation. Of course, this has disrupted the symmetry. I will do the same thing on this side, which turns out to be pretty trivial thing to do, because you will be subtracting 3 by 2 times this column from that. Now remember, all these things are same, so it just becomes symmetrized. So this minus 11 is not affected because you are subtracting a multiple of 0. This 6 now becomes 0. And all this, some of these things have changed, these things have changed. So, but I have successfully turned one of diagonal entry into 0. So here I use the fact that one of these two diagonals happens to be 0. Now had this been 0, no problem, I would have subtracted a suitable multiple of this from this and done the same thing on the rows. So as long as at least this or this is non-zero, I can always turn the off-diagonal entry into 0. Now this technique will not work if both the diagonal entries corresponding to a non-zero off-diagonal entry happens to be 0. So I have taken a very simple example which gives the epitome of that problem. I have this non-zero off-diagonal entry, the two corresponding diagonal entries, both of them are 0. Well, what do? Very simple. All that I do is I just make them non-zero using this. Then use this non-zero to make that back into 0. So what I do is I add this entry, this row to this. So what do I get? I will do Q1A. So this will become 1. And since this is 0, this remains 1. Of course, this destroys its symmetry. I will get the symmetry back if I post multiply by Q transpose, which will basically add this column to this column. This being 0, this will remain unaffected, this will become 2. So observe that I have achieved what I wanted to achieve. I now have a non-zero element in the diagonal corresponding to my target of diagonal entry. So now I get back to my original prescription. I subtract half of the first row from this, turning this to 0. So I will call that Q2. Half of that, so this becomes 0, and this becomes minus half. To preserve the symmetry, I will have to do it Q2 transpose, which is hardly any work anymore. I will subtract half of this from this. There is no work, so I basically turn it into 0, and I am done, and I have made it into a diagonal matrix. So using these two techniques, you can systematically start killing all the off-diagonal entries. You just have to proceed systematically, making sure that you are proceeding from one end to the other. Otherwise, you run the risk of you make something 0, but in a subsequent step, that off-diagonal entry pops back into some non-zero quantity. So just do it in a systematic way from one side. There are various ways in which you can start. Just make sure that when something is 0, everything before that is also 0. So just by looking at a matrix, it is quite easy to determine this order. And that's it. Now, by this method, I am getting my D matrix. But what happens to my Q matrix? Well, here I can see that this is my Q matrix, this is my Q transpose, that is true. But naturally, I would like to have it as a single matrix instead of just a list of Q1, Q2, and then I have to do the product. Well, the technique is pretty simple. We already know whenever we pre-multiply a matrix by something, we can always keep track of that by simply appending an identity matrix to its right. So I append an identity matrix to its right. So in general, what I am doing is I am starting not with A, but AI. And now whenever I pre-multiply by Q, remember, pre-multiplication kind of distributes over its column. So this is basically QA Q times I. So this I turns into the Q. Now, of course, I also have to post-multiply. So when I post-multiply, I am working with columns. Then simply remember that whatever you do with the post-multiplication thing, you remain confined within this part. So eventually it will become Q transpose on this side, QA Q transpose, and this side will show only the effect of the row transformation. So you can very easily read up your Q also from this operation. And this is what Rao Bhim Shankanam has given as their algorithm 9.3.2, but they have made a horrible mess of the entire thing. So if you really want to do it for a given matrix, you can just see how easy it is, because you locate a non-zero entry, non-zero off diagonal, and you kill it, and you proceed systematically through the entire matrix. That's it.